So the goal was to find the area of the rocket ship and the moon. We'll start with the rocket ship, that light blue triangle. If we let the radius of a large circle be 10, then the area of the rocket ship is 50. That's done. Now we just need to find the area of the moon. Find the moon's area. Let's find the areas of region A, B, and C in this picture. Because the moon that we're looking for, the crescent moon, will be the area of the entire small circle minus those parts in the picture, A, B, C, and 50. All right, so first let's find A, using the sector that is 1/4 of the large circle, highlighted here in pink. 1/4 of the large circle is equal to region A plus 50. So if the large circle's radius is 10, then 1/4 of its area is 1/4 of pi times 10 squared, pi r squared. That's equal to 1/4 of 100 pi, which is 25 pi. So 25 pi is equal to region A plus region 50. Therefore, region A's area is 25 pi minus 50. All right. So now we have region A. Let's go on and find region B and C. We'll use the bottom semicircle of the small circle, highlighted here in pink. Part of the region is 50, the other parts are B and C. So the semicircle is 50 plus B plus C. Semicircle's area is 1/2 of the small circle. So 1/2 of pi radius squared for the small circle is equal to the regions 50 and B square units and C square units. So we need to know the radius of the small circle. Let's move over here to the left in red and green. Small circle's radius is highlighted there. The triangle is a right triangle with sides 10 and 10. Remember from Pythagorean's theorem that a squared plus b squared equals c squared. So 10 squared plus 10 squared equals the hypotenuse squared. And the hypotenuse, you can see in the picture, is actually 2 of the radii of the small circle. So the hypotenuse is 2r. So a squared plus b squared equals c squared is 10 squared plus 10 squared equals 2r squared. That gives us 200 equals 4r squared. Divide both sides by 4, and r squared equals 50. So r is equal to the square root of 50. So now we can go back up to our equation where we had 1/2 times pi times the radius squared. Put radical 50 in there, and we have 1/2 times pi times 50. Half of 50 pi is 25 pi. Now we know what b plus c is. The area of b and c together is 25 pi minus 50. So to find the moon's area then, we'll begin with the area of the entire small circle, and we'll subtract those white regions, A, B, C, and 50. The small circle's radius is the square root of 50, so the small circle's area is pi times that radius squared. We'll subtract A, that we already found previously. We'll subtract B and C, that we already found previously. And we'll subtract 50. When you subtract and combine all your like terms, this expression simplifies to the area of the moon being just 50. All right, so the rocket ship's area was 50, and the moon's area is 50. And that's the exciting conclusion right there, believe it or not. We have a curved region being exactly the same area as the region bounded by straight edges. This was first proved by Hippocrates, probably saying that wrong, the Greek physician from around 400 BC in Greece, after whom the Hippocratic Oath is named. He derived this proof in a futile attempt to prove the classic problem of squaring the circle. You can look that up if you want to see what that is. But it was a classic problem in ancient Greece geometry. It wasn't until more than 2,000 years later, in approximately 1880 something, that it was finally proven that it's impossible to do. You cannot square the circle. But Hippocrates tried, and in the process, he came up with this problem and some variations of this problem. And this problem is called the Loon of Hippocrates, because it looks like a moon. All right, as is the case with many ideas in math, there are many ways to prove this idea, the Loon of Hippocrates. We just did it for a single case when the radius of a large circle is 10. But to actually prove it for every case, we'd have to use variables. If you want to see what that's like, if anybody tried it, our proof, one of many proofs, will follow the same structure that we just did when the radius was 10, but we're going to use a variable instead. Here we go. What's the rocket ship's area? What's the moon's area? You can see the large circle's radius is now m. This will represent every case. So the triangle's area is 1/2 times base times height, which is 1/2 times m, which is 1/2 of m squared, or just m squared over 2. We now have the area of the rocket ship in the general case. Now let's go on and find the moon's area. Okay, to find the moon's area, again, we'll find the areas of region A, B, and C. And we already know the triangle's area, which is 1/2 m squared, or m squared over 2. All right, so the moon will be the entire small circle minus those white parts. So let's find the white parts. First, we'll begin with A. We'll use the sector of the large circle, which is 1/4 of the large circle. And the math that follows here is exactly what we did before, except with variable expressions. So there's the area of region A. Region B and C, we'll find the same way. 1/2 of that small circle is the triangle plus B and C. So 1/2 of the small circle's area, we need a small circle's radius. You can pause if you want to follow that. The small circle's radius is m divided by the square root of 2. We substitute that in. We find that the area of B and C together is pi m squared over 4 minus m squared over 2. And now that we know that, we can find the moon's area. The moon is the entire small circle minus region A, minus region B and C, minus the triangular rocket ship. There's all the expressions, and it all works out. The area of the moon is m squared over 2. So we've proven the Loon of Hippocrates. In this case, the loon's area will always be equal to the area of that triangle, that right triangle.